Let us first discuss aliphatic amines. Aliphatic amines are classified into mainly primary amine contain a monovalent NH2 group, secondary amine contain a divalent NH group, and tertiary amine contain a trivalent N group, N with the trivalency connected to alkyl groups. The bond angle in ammonia is 107 degree, and that in trimethyl amine is 108 degree, and this is due to the steric repulsion between the methyl groups, which will try to move apart, increasing the bond angle. Now, naming the last letter E of the parent hydrocarbon is discarded, and then the suffix amine is included. Now this amine is named as propan 2N1 amine. Preference goes to the carbon connected to the amino group. Then 1, 2, 3 on second carbon the double bond starts, so it is 2N1 amine, and the parent is propene. Propan, it is propen, P-R-O-P-E-N, propan 2N1 amine. P-R-O-P-E-N, propan 2N1 amine. Now, the case of aromatic amines, amino group being connected to the benzene ring. So it is benzene plus amine, the last letter E is omitted, and it is called benzene amine, or the trivial name is aniline. Now, when there is a methyl group, it is given preference, and 1, 2, 3, 4, 5, 6, it is 2 amino toluene, being the parent being toluene. And then we have another compound where the amino group is given preference 1, and the halogen is given preference second preference, so that number 1 starts on the carbon connected to the amino group, and the number 4 starts on the carbon connected to bromine. So it is 4-bromo-benzamine or 4-bromo-aniline. In this compound, the preference goes to OH group, and so we number the carbon 1 as the one connected to OH group, and on carbon 2 there is amino group, so it is 2 amino propan 1 ol. Now there is a question: write the structures of different isomeric amines with the formula C4H11N. You write 4 carbon atoms in a chain, and when you place a mirror here, these 2 carbons are similarly placed, and these 2 carbons are similarly placed. So we can connect amino group to this carbon or this carbon, we get 2 different isomers. And the first one is called butane 1 amine, because 1 is given to carbon connected to amino group, number 2 is given, number 3 is given, and number 4 is given like this. And so it is butane 1 amine, and here again numbering the carbon atoms 1, 2, 3, 4, where minimum number is given to the carbon connected to amino group. If you are numbering in this direction, this number will be 3, and if you are numbering in this direction, this number will be 2, so that it is butane 2 amine. Now you write 3 carbons in a chain, and then connect the 4th carbon to the middle carbon, because when we connect the 4th carbon to the end carbon, we get this structure. And there these 3 carbons are similarly placed and this carbon is different. So two different primary amines are possible, and this one is 1, 2, 3, where amino group is connected to this carbon. 2-methyl propan 2-amine, and then we can connect amino group to either of these carbons, so that we get CH3CH, CH2, NH2, CH3, and it is 1, 2, 3, 2-methyl propan 1-amine, or we can call it propan-amine. Now then include nitrogen also in the chain CCNCC, then it's a secondary amine. Then completing the valencies with the hydrogen atoms, we get CH3, CH2, NH, CH2, CH3. It is N-ethyl, means ethyl group is connected to nitrogen. This N stands for nitrogen, where the ethyl group is connected, and the parent compound is called ethanamine because the parent contains 2 carbon atoms, so it is ethanamine. So we consider it as a substituted derivative of ethanamine, and when this particular arrangement is considered, the valencies are being connected to, remaining valencies being connected to hydrogen. We get CH3, CH2, CH2, NH, CH3. Now here the highest carbon alkyl chain is this one, and hence the parent is propane, so it is N-methyl propanamine. Then you connect 3 carbon atoms in a chain, connect nitrogen and then the 4th carbon. We get CH3, CH, CH3, NH, CH3. And here it is an N-methyl propanamine, but the amino group is connected to carbon 2, so it is N-methyl propan 2-amine. Now these two are considered as position isomers because the position of the amino group is changed. Now these two are considered as also position isomers because the NH2 group is connected to position 2 here and position 1 here, and again there is a difference in the here there is position isomers. There is no difference in the arrangement of carbon chain, so these two may be considered as position isomers. But when we consider 1 and 3 or 2 and 3, there is a difference in the arrangement of carbon chain. So 1 and 3 or 2 and 3 are considered as chain isomers and also position isomers. Now a last isomer is obtained in this particular arrangement of carbon atoms. Now it becomes a tertiary amine, and here we have the parent as ethane, ethanamine, N-methyl, N-methyl, or N-dimethyl ethanamine, that is a compound. Now here is a change in the nature of the functional group, and so when we consider the previous isomers and this one, there is functional group isomerism and also chain isomerism. Now here also, when we consider this one and this one, 4 and 5, there is functional group isomerism because this is a primary amine, this is a secondary amine. So all the isomers show mainly three types of isomerisms: chain isomerism, position isomerism, and functional group isomerism are shown by the various isomers. Now coming to the preparation of primary amines, the reduction of nitro compounds can produce primary amines: lithium aluminum hydride, then hydrogen palladium in a solvent like ethanol, and another reducing agent is tin and HCl, which can produce hydrogen. Then iron scraps of iron and hydrochloric acid are also used as reducing agents. When you use scrap iron and hydrochloric acid, the initially formed ferrous chloride, that is Fe plus 2HCl, giving FeCl2 plus H2. The ferrous chloride can hydrolyze FeCl2 plus H2O, giving FeOH twice plus 2HCl. So altogether we need 4 hydrogen atoms, so 2H2O. This hydrochloric acid produced can increase the reactivity, so a small amount of HCl is needed, and there CH3NO2 plus 6H giving CH3NS2 plus 2H2O, so that these oxygen atoms are reduced to water or converted to water, and 2H atoms connect to nitrogen, so that the valency of nitrogen becomes 3, and we get methylamine. So nitromethane on reduction with tin and HCl, or lithium aluminum hydride, or hydrogen palladium and ethanol, or tin and HCl, or Fe and HCl. Iron scraps means iron in the form of tin sheets obtained by scrapping the iron rod or cutting the iron rod with a knife, so that we can get small filings, small sheets, thin sheets of iron which are highly reactive. Then ammonolysis of alkyl halides is another method. This is not a convenient method because we get a variety of compounds. For example, reaction between CH3Cl methyl chloride and ammonia. Ammonia being acting as a nucleophile, it attacks the alpha carbon, so it is an SN2 reaction. We get CH3NS2 and HCl. Now here ammonia forms CH3NS2. Again the nitrogen contains lone pair, so like ammonia, CH3NS2 as a lone pair and can act as a nucleophile, so that this methylamine produced can react with another molecule of CH3Cl. Again an SN2 reaction where we get a secondary amine, dimethylamine, and this dimethylamine can again react with the CH3Cl, again a nucleophilic reaction, SN2 reaction, we get trimethylamine and HCl, and then this trimethylamine can react with the CH3Cl. It cannot be considered as an SN2 reaction, but again a nucleophilic attack by this lone pair over this methyl and removal of this Cl as Cl negative, and we get the quaternary ammonium salt, tetramethyl ammonium chloride. We know ammonium chloride is NH4 positive plus Cl negative, and all the H atoms are replaced by methyl groups, and that is called a quaternary ammonium salt, quaternary ammonium chloride, tetramethyl ammonium chloride it is called. Now the order of reactivity of alkyl halides with ammonia is in the order Ri, alkyl iodide, greater than alkyl bromide, greater than alkyl chloride, greater than alkyl fluoride, and this is the order of increasing bond strength. So alkyl iodides are easily broken, so that it is highly reactive with ammonia. Now reduction of nitriles is another method. The reducing agent can be lithium aluminum hydride, hydrogen and nickel, or palladium or platinum. Then sodium amalgam and ethanol. Sodium dissolved in mercury and then the solvent being ethanol. So all these reducing agents can reduce a cyanide or nitrile to the corresponding primary amine Rc triple bond N 4H, lithium aluminum hydride RCS2NS2. So in the case of nitro compounds and again nitriles or cyanides, lithium aluminum hydride is a common reagent. So reduction, we need 4 hydrogen atoms, 2 for this carbon and 2 for nitrogen. 2 pi bonds are broken and we get dually sigma bond CH2, sigma bond NS2, RCS2NS2, a primary amine is obtained. Now reduction of amides, the reducing agent again lithium aluminum hydride. CD-CO bond is completely broken. 2 H atoms come here and 2 H atoms come here, so that it becomes CH2 and NS2, and then second stage is there, that is hydrolysis for hydrolyzing away the aluminum part of the final product, and then we get RCS2NS2. When you examine the mechanism, we will be getting a complex where aluminum is bonded to this oxygen atom, so that this linkage should be broken with water, and 2 H atoms come in contact with this carbon, and the OAL part attaches to H and it is removed. So hydrolysis is necessary according to the mechanism of this reduction reaction. Then there is a name reaction which is important, that is Hofmann bromamide degradation. An amide RCONS2 is reacted with sodium hypobromide NaOBr, sodium hypobromide. Now sodium hypobromide is prepared by the reaction between sodium hydroxide and bromine under cold conditions in dilute medium. We get sodium hypobromide, and here the net reaction is the connection between CO and oxygen of NaOBr. So CO and O of NaOBr is converted to carbon dioxide gas, and then when O is removed we get NaBr, and when CO is removed we get RNH2. Now, so that is a simple reaction, again an important reaction, Hofmann bromamide degradation. Degradation means decreasing the carbon number. Here one carbon atom is lost as a molecule of carbon dioxide, and hence it is called a degradation reaction. Now coming to the physical properties, lower aliphatic amines are soluble in water due to hydrogen bonding. The NH2 group forms hydrogen bond with the oxygen atom of water, so that they are soluble in water. Now higher or heavier members are insoluble because the alkyl part becomes larger in size, higher in molecular mass, and then non-polar character and van der Waals force of attraction, which are not possible with water, and so the alkyl part becomes insoluble, and so the whole compound becomes insoluble as the molecular weight increases as the size of R increases. So van der Waals forces will not operate with water, so heavier members are insoluble in water. Now when we consider an alcohol and an amine of comparable molecular mass, so for example ethanol and ethylamine, they are having nearly same molecular mass. Their ethanol is more soluble in water than ethylamine. Why? Because the nitrogen atom is having a lower electronegativity than oxygen atom. The electronegativity of oxygen is 3.5, that of nitrogen is 3, so that the strength of hydrogen bond will be stronger when the atom is oxygen in ROH, alcohol, C2H5OH or CH3CH2OH. So these stronger hydrogen bonds are formed generally by alcohols and water, and so alcohols are more soluble in water than amines of comparable molecular mass. Now primary amine can form 2 hydrogen bonds and secondary amine can form only 1 hydrogen bond, while tertiary amine forms no hydrogen bond. So boiling points of isomeric amines will be in the order primary, greater than secondary, greater than tertiary. So here hydrogen bond is formed between amine molecules. So when we consider 2 amine molecules, primary amine molecules are NH, NH, then N hydrogen bonded to H, H, R, and this also can form hydrogen bond with nitrogen. So a primary amine can form intermolecular hydrogen bonding using its 2 hydrogen atoms. So there is larger association between primary amine molecules, while secondary amine contain only 1 H. There is one NH group as the functional group of a secondary amine, and so it forms only 1 hydrogen bond. And when we consider tertiary amine, there is no hydrogen atom on nitrogen, so there is no hydrogen bonding. So association is greater for primary amine, and then comes secondary amine, and least for tertiary amine, so that N-butylamine has a boiling point of 350.8 Kelvin. Diethylamine, a secondary amine, has a lower boiling point of 329.3 Kelvin. And when we consider a tertiary amine of comparable molecular mass, its boiling point is less, 310.5 Kelvin. So association due to hydrogen bonding among amines is largest in the case of primary amines. Now coming to the basicity of amines. Now an amine RNS2, for example, a primary amine, reacts with water producing RNS3 positive and OH negative. Now the equilibrium constant Kb is given by RNS3 positive into concentration of OH negative divided by concentration of undissociated or unreacted RNH2. And greater the value of Kb, greater will be the concentration of OH negative, and higher will be the base strength of the base or amine. Now there is a parameter called pKb, that is minus log Kb, so that it is log 1 by Kb. So as Kb increases, pKb decreases, so a higher value of Kb will be a higher value of Kb will lower the value of pKb. A higher value of Kb will lower pKb. So lower the pKb, higher is the base strength. Just like the case of acids, higher the value of pKa, lower is the acidity, and lower the value of pKa, higher is the acidity. Here also, lower the value of pKb, higher is the basicity, and higher the value of pKb, lower is the basicity. Now three branches of amines show basicity variation depending on the circumstances. In the gaseous phase, inductive effect is the only deciding factor of basicity, so that a tertiary amine, trimethylamine, with a greater I effect will be having a higher basicity than a secondary amine and a primary amine. See here, a tertiary amine with a higher magnitude of inductive effects the plus effect of 3-methyl groups will push the electron pair towards the nitrogen atom, so that this nitrogen will be readily removing its lone pair towards H positive, so that basicity increases due to plus effect of 3-methyl groups. The nitrogen will be more ready to donate its lone pair to H positive because it is receiving electron density from the methyl groups by plus I mechanism. So higher the plus I effect, higher is the ability of nitrogen to donate its electron pair to H positive because its electron density, the electron density around nitrogen is increased by the inductive effect of alkyl groups. So tertiary amine contain 3 alkyl groups, so the magnitude of the inductive effect is larger and higher is the electron density around nitrogen and higher is the tendency for the nitrogen to donate its electron pair to an H positive, and hence higher is the basicity of the amine, while in the case of secondary amines there are only 2 methyl groups, and so the magnitude of inductive effect is decreased, and so electron density around the nitrogen is decreased. And when we come to methylamine, a primary amine, the electron density around nitrogen is least, so it will be having a least tendency to donate its pair of electron towards H positive, and so it will be having least basicity, and this happens in the gaseous phase. But when we consider the amines in a solvent medium, in solution, 3 factors play important roles in deciding the basicity, that is inductive effect of alkyl group and solvation of the protonated base and steric effect. So these are the important factors, aspects which decide the basicity of amines in solution. One is inductive effect of the alkyl groups, and then solvation of the protonated base and steric effect. Now here RNS2 reacts with H2O giving RNS3 positive, and this is the protonated species. This is also called conjugate acid. And this conjugate acid is solvated. For a primary amine, the conjugate acid has 3 H atoms around it, so there are 3 hydrogen bonds, and for a secondary amine there are 2 H atoms around it in the protonated base, that is conjugate acid, and the 2 hydrogen bonds are there. And when we come to a tertiary amine, there is only 1 hydrogen in the protonated base or conjugate acid and only 1 hydrogen bond with water. So the stability of the solvated protonated base is in the order primary greater than secondary greater than tertiary. In the case of methylamine, dimethylamine and trimethylamine, steric effect is less important, and the basicity is decided mainly by the inductive effect and solvation of the protonated base. Because we have now seen that the primary amine, the conjugate acid of primary amine is more solvated, and again the secondary amine is having only 2 hydrogen bonds. Again it has 2 alkyl groups, so the inductive effect of 2 alkyl groups increase the electron density around the nitrogen than in the case of a primary amine, even though the conjugate acid is solvated by 3 hydrogen bonds. The secondary amine is having an optimum value of solvation and inductive effect, so that in the case of methyl amine, dimethylamine and trimethylamine. The order of basicity is dimethylamine greater than methylamine greater than trimethylamine and ammonia. Now from this order it is evident that protonation protonated conjugate acids and its solvation and again inductive effect are more important. And in the case of methylamine, even though there is only one alkyl group, the conjugate acid is highly solvated, so solvation is important as well as inductive effect is important, and these two effects are optimum, not in the sense maximum, but it is optimum, near to maximum in the case of secondary amine, and hence secondary amine dimethylamine is having higher basicity in a solution than methylamine and trimethylamine, where the solvation is least even though the inductive effect is maximum. Now when CH3 becomes C2H5, steric effect also gain importance. There the order is again diethylamine having the highest basicity, and then triethylamine is having the highest basicity, and then finally comes ethylamine, and then lastly ammonia. Now in the case of triethylamine, the nitrogen atom is connected to 3 ethyl groups which are bulky. So these ethyl groups can repel each other, and again there is lone pair bond pair repulsion. This lone pair can repel this bond pair, and this bond pair. So 3 lone pair bond pair repulsions are there. So these repulsions will try to avoid the lone pair. When an H positive connects to this nitrogen using its lone pair, we get NH C2H5, C2H5 and C2H5. So that the lone pair bond pair repulsion is avoided. So the bonds are now free to move apart due to steric effect of the ethyl group. So relief from steric strain is obtained when the lone pair becomes a bond pair by coordination with a proton H positive, so that the molecule will be showing a higher tendency to donate its lone pair to H positive to get relief from steric strain. So triethylamine is second in basicity in the case of the series diethylamine, triethylamine, ethylamine and ammonia. So these two examples they give the importance of inductive solvation of the conjugate acid and steric effect in deciding the basicity of various classes of amines. Now that is enough. Thank you.